Albert Einstein is often considered one of the greatest minds of the 20th century, and he was a pretty fascinating dude. And the thing I find most fascinating about him was that he was explaining very complex theories, very difficult phenomena, and he had the ability to break it down and explain it using some of the very simple things that see in your day-to-day life. So he could break down very complex concepts into things or analogies that you could relate to very easily. That's why all of his papers are very widely cited. So if you look at some of his publications, and if you make a timeline of some of his publications. So this is a timeline of some of the major accomplishment of Einstein, and there are many of his there are many of things you can draw on these timeline. But a few things that stand out was this year 1905, and this is called the wonder year in the life of Einstein. And he published three breakthrough papers. Each of them defined a whole field of their own. So firstly, he proved the existence and he proposed the existence of a photon, which is the basic particle which carries all of electromagnetic radiation. So his interest in electromagnetic radiation really started in 1905. He also published a paper on Brownian motion, and one of the things that came out of that paper was that it related the diffusion coefficient to the mobility and how it relates to the temperature using this formula where your diffusion coefficient is related to the mobility by a multiplication factor, which is given by this kT by Q. And this is something that we use in semiconductors. So even though Einstein was studying Brownian motion in gases and how gases diffuse, this is something that we use in semiconductors. In 1905, he also came up with the special theory of relativity. And in fact, Einstein is most famous for his theory of relativity. And a large part of between 1905 and all the way till 1915, he spent on developing this theory of relativity further. And in 1905, and he was, a lot of his time was consumed in this theory of relativity, even though he was doing and publishing other papers. But the real breakthrough came in 1915, and he published General Theory of Relativity, which shows that time and space are not exactly independent things, and they are related to each other. And this was a major breakthrough. But after 1915, he returned to some of his earlier work that he had started on electromagnetic radiation. And in 1917, he published a paper which is titled The Quantum Theory of Radiation. And this is what I want to talk about in this video. And this paper essentially laid out the foundation of how a laser would work. Even though Einstein did not invent the laser. In fact, if you look at the years he was active, these were much before the laser was invented. So he was active between 1905 and 1936. Most of the semiconductor theory was developed if you look at in the same timeline, when was semiconductors developed. So semiconductor was developed in the 1950s. So Einstein's work for sure was predated, was pretty much before semiconductor devices became popular. And in fact, the first lasers were also not realized in semiconductor. The first lasers were made in this material called ruby, and then there were laser based which utilizes these gases such as helium neon or gases like carbon dioxide. So what semiconductor this was, what they enabled was in the field of laser was that they allowed these lasers to be made very compactly or made very efficiently, and that's what semiconductor lasers allowed us to do. But Einstein for sure was not the one who was studying about semiconductor lasers. He was in fact just interested in studying how light interacts with matter, and he described that in this classical publication, and this was published in 1917, and the paper is called Zur Quantentheorie die Strahlung, and I'm sure I'm pronouncing it wrongly, but what it stands for in German is on the quantum theory of radiation. Now what Einstein said was, let's say you have a gas or you have another form of matter, and the atoms or the electrons in these atoms could be at two energy levels. They could be at this energy level E1, or they could be this energy level E2, which is at a higher energy as compared to E1. And now you shine photons on this gas with a certain frequency, and now he said now there are three possible things which can happen. So the very first thing that he said that can happen is that these photons can get absorbed. So these photons can get absorbed in this by these electrons which are present at that energy level E1, and then this can get absorbed, and this electron will take that energy and go to this energy level E2. And he said that the probability of this happening is, of course, it should be proportional to the number of electrons I have in the energy level N1. So it should be proportional to the number of electrons I have over here. It should also be proportional to the flux or to the density of my incoming photons. That makes sense, because more the number of photons I have, there's a higher probability that a photon can interact with these electrons and take them to a higher energy level. And then he said this is all related by a proportionality constant, and he called this constant as B, and he gave it a subscript of 1, 2, because this involves the transition from energy level 1 to energy level 2. And so he said the net rate of absorption should be essentially given by this formula. And of course, it was Einstein who was naming, who was deriving this. So these coefficients are essentially, this coefficient B is called as Einstein coefficient. Then he said now there could be another process which could be happening. So there is absorption. But now if I have excited this electron to energy level E2, so I have excited let's say a few electrons to energy level E2. Now what could happen is that these electrons, they are in an excited state, so now they can come down, and they would like to essentially come down in energy level, and they can release this energy out in the form of a photon. And he said again, this process is what he called as spontaneous emission. The reason why it's called spontaneous is because these electrons at the higher energy state, they want to come down to this low energy state on their own. So there's nothing which is triggering them to come down. They have we excited them to this higher energy state, but once they are there, they spontaneously like to come down and emit out and they can release out this energy in the form of this photon. So again, he said that this process should be proportional to the number of electrons I have in the higher energy levels. So he said this should be proportional to N2, which kind of makes sense, because the more the number of electrons you have at the higher energy state, the more is going to be the rate of your spontaneous emission. And this process is pretty much spontaneous, so it does not depend on anything else. And he gave, so the net rate could be given by N2 into this coefficient A to 1, and he gave the subscript to 1 because it's involving a transition from the level 2 to energy level 1. And then he said, wait, there are these two processes, wait a minute, there could be something else. And this was a real genius in this paper, and he derived or he gave a few arguments that why this third process could be happening. And this third process is, what is the defining feature of all lasers and all nice things about them. And he said there could be a third process going on, and this third process is called simulated emission. And what he said was,